I'm an engineer and a scientist. As an engineer, I use computer models to design and make things. As a scientist, I look at the data to see if my computer models are correct. So what we did in the Centre for Environmental Research and Earth Sciences is that we looked at the data from 20 million radio balloons. Now, we then said, can we look at this data and see how we can use it to check the computer models? And we found there's two types of balloons. One, the average weather balloon does about 100 measurements as it goes up to the stratosphere. But the ozone sondes, which measure ozone, they do a measurement about once every second. So you have maybe 4,000 or 5,000 measurements on each sample. But all of the climate models, and by the way, nobody in the climate model community bothered to check the data to see if their models were correct, which I find very bizarre. But all of the model community, what they do is they divide the Earth into a number of little boxes. So on a horizontal scale, the boxes are about 1,000 miles long, and on a vertical scale, they're about less than a mile in height. And what they do is they make a number of assumptions about how the air behaves within each of these boxes. So the first assumption that they make is that the air in each box is in a state which we call thermodynamic equilibrium, and I'll explain that in a few minutes. And they assume that on a horizontal scale, the air in a box is in equilibrium over a distance of 1,000 kilometers, or 1,000 miles rather, but on a vertical scale, only in equilibrium of about less than a mile. And they also assume that the different boxes are not in thermodynamic equilibrium with each other. Because if it turns out that the boxes are in thermodynamic equilibrium with each other, all of the assumptions of the climate models collapse. Because Einstein and his co-authors over 100 years ago showed that if a system was in thermodynamic equilibrium, that if you put in a greenhouse gas into the system, it would absorb more energy, but if it's in thermodynamic equilibrium, it emits more energy. So increasing the level of greenhouse gases will increase the rate of absorption, but also increase the rate of emission. So there's no net change due to the radiation. So if it turns out that the assumption that the different boxes aren't in thermodynamic equilibrium is false, then the whole theory of man-made global warming collapses. So how do we know if something is in thermodynamic equilibrium or not? Well, what you do is you take a system and you do all the measurements of the different parameters involved. And if you can describe the system in what's called an equation of state, with using these parameters, then we say the state is in thermodynamic equilibrium. So in other words, obeying an equation of state is one side of the coin of being in thermodynamic equilibrium. They're both different sides of the same coin. So for the air, the equation of state is this. It's called the ideal gas law. And this is the equation that's used by the climate modelers in treating the different boxes as being in thermodynamic equilibrium. What the equation of state doesn't tell you, and you can see them down there, it tells you the relationship between the different parameters, but it doesn't tell you how much energy it would take to change the temperature of a system. For that, you need to know the heat capacity of the system. And it doesn't tell you anything about potential energy. So in other words, if I take a cubic meter of air and lift it up and keep it at the same temperature and pressure, it would obey the same equation, but it would have gravitational potential energy because it takes energy to lift it up. that's not reflected in the equation of state. So this is normally how climate scientists and atmospheric scientists describe the atmosphere. So what you see is, this is the same data, or data as you say. I don't know why you mispronounce data. If you see on one side there, I've plotted the temperature versus pressure, and on the other side, the temperature versus height. So the lower troposphere is where the temperature drops off at about 6.5 degrees per kilometre as you go up through the atmosphere. And up until they had good quality balloons, everybody assumed that that would continue right up to to space. And when they started getting balloons up and being able to measure at the height there where we have the boundary between the tropopause and stratosphere, they were convinced that their thermometers were inaccurate, and they spent an awful lot of time trying to correct the thermometers until they finally realized that this was a real phenomenon. So this is something that, as a chemist, I thought was dead obvious to do, but the equation of state can be rewritten in a different form, called the molar density form. And this form has been used by chemists for hundreds of years to determine the molecular weight of new gases. So we said, what happens if we describe the atmosphere in terms of molar density form instead of the energy form? And we were the first, and still the only people to have done this. And when we did that, we got a big surprise. What we found was that if you plot the molar density versus pressure, you get these two straight lines. Now, that means that the atmosphere in the troposphere, that's the lower bit, is obeying an equation of state. So that means it's in thermodynamic equilibrium. And when you get to the tropopause, it turns into another straight line. Now, this is quite common in studying materials. If you can describe it in terms of one equation of state and then it changes into another equation of state, we call it a change of phase. For example, you can describe water using the gaseous water using the gas laws, but then when it turns into liquid water, you have to use a different equation of state. Now, we studied all we studied all the different weather balloons from all around the world, and we found that this phenomenon occurred in all of them. The only difference was that in the tropics, the change of phase occurred at a higher altitude, and in the Arctic and polar regions, it occurred at a lower altitude. So when we were here in Tucson 5 years ago, we made this little video, which I'm going to show you. And the idea, if you look at it, is the orange line there shows what would have happened to the temperature if the phase in the tropopause continued down to ground, and the green line shows what would have happened when it... thank you, Willie, a lifesaver. So we made a video for the entire year of all of the radio balloon data for Tucson for 2018. And the reason that I do this video is that looking at a static graph like that, you don't see any changes. Now, in the models that they're using, if the different boxes are isolated from each other, if you put energy into one of the boxes, it would kind of stay there. But if they're in thermodynamic equilibrium, you put energy into one box, all of the boxes will change because all of the energy will be distributed throughout the system. And when you look at the video here, all that I'm going to show you is to watch the behavior, of the position of the boundary layer, that moves up and down, but also the temperature. If it moves to the right, the temperature is increasing. If it moves to the left, the temperature is decreasing. And what you will see once you watch the video, I'll start the video, I think. It's all synchronized. So in other words, if a change occurs, if the troposphere is warming up and the temperature is moving to the right, the tropopause moves down, but the tropopause moves in the opposite direction. So in other words, when the troposphere heats up, the tropopause cools down. When the troposphere cools down, the tropopause heats up. And it does so in a synchronized way. So that synchronization shows that it's thermodynamically connected. The idea that all of these boxes are not in thermodynamic equilibrium is contradicted by this data. So that's the first assumption. Now looking at the second assumption, when back in the, I don't know, 17 something or other, Hadley was looking at trying to explain the trade winds. And so he came up with this idea that what happened was the very hot temperatures landing on the equator heated up the atmosphere, and that this hot air then rose up. And then as it rose up, it started to move towards the poles. And then as it was moved towards the poles, it cooled down, and you got this circular phenomenon. And they came up with three different types of circular cells. You had the Hadley cell, Ferrel cell, and the polar cells. But all of this theoretical stuff was based on ground measurements. And again, nobody bothered to check where this is true or not. So I'll just show how we checked it. But first of all, I just want to explain what's meant by mass flux. So if you take a square meter and you measure the air flowing through it and what weight of air that is, that's the mass flux. So in the weather balloons, they give you the speed of the air and they give you the direction in which it's going. So you can use this to calculate the mass flux. So we said, fine. So can we use this to check the idea of the Hadley cells and that? And it turns out that you can. So we published a paper 2 years ago. I give the reference at the end of this section. And what we found was, well, first of all, I will go over here. So if you take a balloon and you launch it up through one of these cells, then if Hadley is correct, you would expect the hot air was rising here in the tropics, and that drags in the air from the colder regions, and then it hits the tropopause. Now, when Hadley came up with the idea, nobody knew the tropopause existed. And it's only 30 years before I was born that it was actually discovered. So that's telling something about my age. Anyway, I'll get into this bit later, but if you send a balloon up through the atmosphere, you would expect the mass flux to flow in that direction down at the lower levels, and then as you go up, at some stage you would shift over and start going in the opposite directions. So since that was available, the mass flux we could measure from the balloon data, we did that, and we got a surprise. There was absolutely no circulation patterns at all. Instead, what the atmosphere was doing, so if we point here, you can see these ones are the lower ones. So what you have here is you have the direction, the north-south direction of the mass flux. And this is the ones at the lower half of the troposphere. These are the ones in the opposite half of the troposphere. And for a Hadley cell, you would expect them all to be flowing, these ones to be flowing in the opposite direction to these ones. But instead what we find is they all flow in the same direction. And a very unusual pattern. What happens is here it's flowing south, then the atmosphere slows down over a couple of days, goes back and forth and so on. So instead of this circular pattern, what's happening is the whole atmosphere is moving like a giant pendulum back and forth. So we have the atmosphere goes one way. After a few days, it turns around and comes back in the opposite direction. And this is for Iceland, but what we found was the exact same thing occurred for all the different stations. So we did, in that paper that we published, we took a station from each of the different 5 climate types, and we found the exact same sort of thing happened. Now, the people said, okay, so maybe it's going back and forward on a daily basis, but over a period of a year it might average out. So we averaged the data over the 5 years for each of the stations, and what you can see is for Iceland, it's again all going in the one direction. For Ireland, mostly going in this direction within the troposphere. Now remember, it's supposed to change here. In Spain, it's going in the opposite direction. In Morocco, again, it's going some weird pattern. But you say, look at this one here in the tropics. That looks like a Hadley cell. It's going in this direction, and then it changes and goes in the opposite direction. But the problem is that it's going in the wrong direction. At ground level, it's going from south to north, not north to south that you would expect from a Hadley cell. And when we published that paper, that's as far as we got. But we've since analysed over 250 of the weather stations in the tropics. And what we found is for these, 82% of them are Hadley, 73 in the northern hemisphere. So the majority are not Hadley cells. And in the southern hemisphere, they're equally balanced. But the problem with even the ones that were Hadley cells is you can see here the mass flux flowing in this direction, the area under the curve, is not the same as the one up above. And if it was a proper Hadley cell, they'd have to be the same. So what we found is for none of them, this worked out. So they don't exist, right? So this is the first part. I'll just give the short summary here. So the idea that, which is essential for the models, that the atmosphere is only in local thermodynamic equilibrium, the data shows that's not true. And then one of the big bits that they crow about when they're talking about their models is that they're able to reproduce the Hadley cells and the Farrell cells and so on, but they don't exist. Right? So there's the papers that we published in the peer review process. Now, this is just a light break. I'm sure you've all seen this video before. How do I get this going?
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we no, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. In that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Okay.
I'm going to discuss.
Oh, sorry. Okay. So, in order to try and explain why is it that the temperature changes when you get to the tropopause, instead of decreasing as you go up, why does it change? And why do we have an ozone layer in the tropopause? So Chapman came up with this explanation. He said, in the tropics, you've got very high levels of high energy UV, ultraviolet radiation, and that can break an oxygen molecule into 2 atoms. And then one of these atoms comes and hits another oxygen molecule and forms what we call hot ozone. It's hot ozone because if you don't take the energy out of it, it'll just disintegrate again. So once you form this hot ozone, it has to be simultaneously hit by another molecule that'll take away the surplus energy and leaving you with a stable ozone. So that is the explanation that's given for the ozone layer. And then what they were saying is this ozone absorbed UV light and that turned into heat, and that's what heats the tropopause. But there is a problem with the Chapman mechanism, and that's this. If you look here, this is the temperature for it. Now I've had to change the orientation, so this is ground level, this is the sky up here, and this is pressure, because Excel only allows me to pull up multiple graphs in this way. So this is the temperature as you go up through the atmosphere for the tropics, and you can see there's a very small amount of ozone there. And then in the mid-latitudes in Huntsville, you can see the ozone level goes up. But in the Arctic winters, in the dark, we have the huge amounts of ozone. So how is it that in the winter, in the dark, with the ozone, we have the highest level and the highest temperatures? Why is that if there's no UV light? So in order to explain this, Brewer and Dobson came up with this idea. What they said was that the UV is formed in the tropics, but there is a circulation in the tropopause that carries all this ozone to the poles. Now, the only justification for this is it's the only explanation they could come up for why there was more ozone in the polar regions. There hasn't been any confirmed looking for this circulation. So we looked at it with our mass flux, and what we found is, again, it doesn't exist. So in other words, what you can see here is here you have the boundary, the so-called circulation. It's going in the wrong direction. Here it's not there at all, and so on. So what we're finding is the same sort of problem that we found with the Hadley cells, and that it doesn't exist. But even if it did exist, there is another problem. If you look from that video that I showed you earlier, you could see that when the troposphere, below the tropopause, is hot, above the tropopause, it's colder. And when it's cold in the troposphere, it's the lower section, it's hotter in the tropopause. And so if you go from north to south, or from the equator to the poles, as in the lower atmosphere, it gets hotter or colder and colder as you go towards the poles, by about 30 to 40 degrees. But in the tropopause, it gets hotter and hotter as you go through the poles. So if there was a Brewer-Dobson circulation, how is it that it's getting hotter and hotter as you go into the polar night? I mean, that doesn't make sense. So that's another thing that shows that the Brewer-Dobson circulation doesn't exist. So just as a brief summary of this then, the Brewer-Dobson disproves the balloon data disproves the Brewer-Dobson circulation hypothesis, and therefore the Chapman mechanism isn't supported either. So what we need is a new localized explanation for the generation of ozone in the troposphere. And we think we have one. But what you need is, these are all the different phenomena that it must explain. How is the ozone produced locally? Because it can't be produced in the tropics. In the solar winter, it's got to be produced in some local way. So, what I just wanted to, this is another new piece that we haven't published yet, and that hasn't been used by the climate modelers. And that's, as I was saying earlier on, one of the things that we don't get from the equation of state is the potential energy of a particular mass of gas, depending on how high up it is. And from the balloon data, we can work out what the potential energy is. I won't bother going into the equation, but you can see if we have a pressure at 2 points and the heights between them, we can work out what the gravitational potential energy is at that spot. And this is for those 3 ones that I showed you earlier. And what you'll notice is that First of all, it's a huge amount of energy. You know, this is in joules, 40 kilojoules for this height. The area under the curve is quite high. But the other thing that we've found is that from day, and I'll show you this in the next few slides, that there's huge variations in the gravitational potential energy from day to day. And the variations are of about the same order as you get from sunlight. And these are totally neglected in all the models, which is quite bizarre. Yeah. So what I have here is I've taken two from the southern, from Summit, Alaska, or Summit, Greenland, and these are a week apart. These are ozone sondes. This is very large number of, they're taken every second. This is why this is a little bit rough here. I could have smoothed them over a minute and it would have been smooth. But what you can see is that the change in the tropopause there and the temperature, as you can see there, it corresponds with a change in the gravitational potential energy. And here what you can see is that if it occurs lower down, there's more gravitational potential energy. And again, this whole gravitational energy is something that hasn't been studied at all, which is interesting. So that's the two. The thing you can see here as well is that for the one where it's hot here, warmer here, it's colder here, and when it's colder here, it's warmer here. That's just for the one station, and that occurs at every station. Here's a comparison for the Huntsville one. Again, you can see the warm, cold, colder, warmer. And again, you see this change in phase all occurs, and it's accompanied by a decrease in the gravitational potential energy, which we're still trying to figure out what that's all about. And again, here in the tropics tends to be the same sort of temperature the whole year round, but there are slight variations. But again, you can see if it's warmer there, it's colder there, and so on. So this is a universal phenomenon that applies all throughout the entire world and all the different climate zones. So now I want to look at this again. So what you can see here is the temperature decreases as you're going up through the atmosphere, and then suddenly you get a rise in temperature. And that corresponds with a change in phase of the water. So the gaseous water changes from being gas into a liquid form, whether it's clouds or rain, but mostly it tends to be clouds. But as soon as that happens, what you get is the release of energy, energy of condensation, and that raises the temperature. And then it starts to drop off again. And here is again the same thing. Here you've got, say, 2 cloud layers and 2 rises in temperature. And this, by the way, some people say that's due to sunlight being reflected off the clouds, but this happens even at night. It doesn't matter whether there's sunlight there or not. You get this same sort of rise. And what I'm pointing out is here at the tropopause, what we find here is a change of the liquid water, the water, gaseous water into liquid. We can find that this looks again like a bigger phase change of something. But what could it be? I mean, we know there's no water there because the tropopause is dehydrated. So thinking about that, I did a lot of work in my earlier science days on cryogenics, and I did a lot of work with liquid nitrogen and liquid oxygen and so on. But if we look at oxygen, at room temperature, it's a colorless gas made up of 2 atoms joined together, 2 atoms of oxygen. But 30 years ago, experiments were done bombarding low energy oxygen atoms against each other, and it formed dimers of oxygen. These are called, it isn't a chemical rearrangement, it's what's called a van der Waal bonding. I'll show you the paper on that in a second. But you get these ones here, and it's worked out what the energy of binding is. But if you take oxygen at room temperature, and you subject it to very high pressures, it turns into forming this van der Waals-type molecules. It's called red oxygen because it absorbs and emits red radiation. And what it is again, it's 4 molecules of oxygen, 4 of these molecules lined up like that to form what's called a tetramer. And then if we take the oxygen and keep it at room pressure but cool it down, then it turns into a blue liquid, sky blue liquid. Now, all scientists said, why is this blue? Why is it turned blue? And the explanation that's given is that in here, in the liquid, there must be tetramers of oxygen that are absorbing the red out of it. And so if you take red out of white light, you end up with blue. So that is the explanation. Now, so this is the paper that was done on the dimers showing if you have low energy collisions of oxygen molecules, you get these dimers occurring, and this is their binding energy and so on. So this is what's called the Maxwell-Boltzmann distribution. And what it says is that this is the speeds, the amount of molecules with given speeds as you measure at a higher temperature, you'll get more faster moving molecules and less slower moving molecules. But if you drop the temperature down, you end up with more of the slower moving molecules and less of the faster moving molecules. And what we're proposing is, and I've done thermodynamic analysis on it, and it's energetically possible, is that if, as you go up through the atmosphere, the temperature cools down, and as it's cooling down, if it reaches a stage where some of these molecules, slow-moving molecules, can now collide to form tetramers, then it's like a condensation. So where we were saying that thing that looked like water condensing, if this happens, then we will get the same sort of rises in temperature. And also, we now have a mechanism for forming ozone without the UV light. Because if you hit one of these tetramers with a fast-moving molecule, you could break it up into 2 ozone molecules and an oxygen molecule. And so this is a possible explanation for why we have this happening. So I think that's about the end of it. Okay. So I got through it in half an hour. I don't know. I maybe went too quick, did I? What I find the bizarrest of all is that all this data to test all of these different models was out there, and nobody bothered to look at it. Yes?
One of the interesting things that I have not heard discussed, and this is after a long time. Okay, that's better?
Yeah.
Okay, good. Picture sunlight. Well, let's just figure that it's September 21st. Sunlight is coming in straight toward the equator.
Yes.
And there's about 220 Dobson units of ozone there. If you go further north, there's something like 350 when you get to our latitude. Now, taking the ultraviolet model, the UV is coming in through a slant height, and it's going through a larger distance of the stratosphere, and could therefore produce more ozone that way.
This is quite true, if that was the case. But what about the polar winter, when there's no light at all? It's in the dark.
Well, of course, in the South Pole, you've got the circumpolar vortex.
Are you convinced? Have you read our paper on mass flux?
Yeah, you're at the South Pole, it just kind of disappears in the wintertime, because it can't flow in or something like that. But in any case,
it doesn't disappear, by the way. When they say you have an ozone hole, what they mean is the level drops below 100 Dobson units.
Oh, yeah.
But it doesn't disappear.
It doesn't disappear. No.
Okay.
No, it remains essentially constant. But anyway, I had never seen any discussion of the actual angle versus the, so you change the slant height.
Yes.
And if you go up to something like...
But the other problem when you change the slant height is that you're putting most of it up into the rarer atmosphere, not through the lower atmosphere.
Well, it's a wide flux, but
Yeah,
I'm
okay.
just talking about
Okay.
the region where this presumably could produce the ozone.
Yep.
There's going to be more ozone, and it's reciprocal cosine, so it would be about the same there.
Yeah. So what you're saying is you could still come up without a Brewer-Dobson mechanism. You're still saying that you could justify the Chapman mechanism in terms of the angle of incidence of the sunlight, which is a valid. I'm not arguing with it. It's perfectly okay. But again, I'm saying there is none in the Arctic winter. There's no light at all. So as Feynman said, all you need is one ugly fact.
Well,
the whole thing is
but what happens if it just stays there? There's no killing mechanism.
So 40, 50 years ago when I was a young scientist, we had the guy who was doing a lot of work on this come to our university and give us a talk on it. And his justification for the Brewer-Dobson circulations, which I believed at the time because I was a young scientist and took authority at their word. So, naive young scientist. Now I'm a cynical idealist. I don't know how that works out. Anyway, the thing he would say was that because it was moving towards a colder and colder region, it was becoming more stable, and that's why it lasted longer. And also the argument was that the UV would also degrade the ozone as well, because it could, just as it could form it, it could break it down. But again, that doesn't explain why the atmosphere in the tropopause where the ozone is getting hotter and hotter as you go through the poles, not colder and colder in his explanation. So all I'm simply saying is I've put forward here an alternative narrative, which I think has a number of explains things. I don't know that that's true, or it's just my guess. Yeah. So I don't know, is there anything else you want me to rant on about?
Well, so be it.
Okay.
Good. Thank you.
Right. Yes.
Thank you. I am still maybe a little confused.
So am I. So welcome to the club.
When I have not been a physicist, I've been a yacht racer, an ocean racer in sailboats, racing across the Pacific Ocean 12 times.
Yes.
And one of the things you first learn about are these big gyres, as they are sometimes called.
Yes.
These are major circulations.
Yes.
They're stationary high pressure zones.
Yes.
The two of them in the northern Pacific, three of them in the southern Pacific, one in the North Atlantic, that's called the Bermuda High, the one in the northern Pacific close is called the Pacific High, the one close to California, one in the southern Atlantic. Okay, are these not Hadley cells?
No.
They are not Hadley cells.
No.
I mean, they appear, once I saw the diagram of how a Hadley cell works, you have massive amount of wind spiraling out.
It is true, but also remember you have those sort of gyres in the tidal effects as well. There are areas there where there is no rise and fall in the tide, So, but what I'm saying is the Hadley cell assumes a continuous circulation.
Well, there is a continuous circulation.
There's
a high pressure.
Yes.
And so the wind is flowing out. It spirals out about 10 degrees.
Yes.
And so how does it, in my own,
Okay,
when I was
so-
doing this, well, let me finish my question then.
Okay.
I was always wondering, how does it refill? Where's all this air coming from?
Exactly.
And then when I sailed across the intertropical conversion zone going to Tahiti,
Yeah.
I found out there's this band going clear around the Earth where the wind is just going straight up. There's the Coriolis force has dropped to zero. In fact, it reverses sign as you cross the equator. So there's no circulation, nothing causing any rotation. So the wind goes straight up, it goes up to the upper atmosphere, and there it refills all these big high pressure zones
Okay.
with
so
air.
yeah. So
Is that not a Hadley circulation?
a Hadley circulation, no, right? What I want to tell you is, you see what I've done here? I have only looked at going from 850 upwards. If you actually look at the ground level doesn't behave in the same way as the rest of the atmosphere. So you have these different patterns that occur due to the Himalayas and various other things getting in the way. And so, whereas I'm saying above the boundary layer, where all the rain and weather occurs, you have this constant oscillation all in the one direction, back and forth. And that's where you need to have the Hadley cells. That's where you need to get the transition between them going from one direction to the other. And that doesn't occur. So what I'm saying is, I look at weather charts every day. I see highs and lows. I'm not saying they're not there. They are there.
Oh, these are the stationary highs.
Yes, okay. But again,
And why are they stationary? They're
the reason,
very permanent fixtures.
my hypothesis, which I haven't put it here at all, is that this back and forth oscillation, if you look at it here, you can count the peaks occurring, and they seem to occur every 15 days or so. I suspect that this is some sort of gravitational tidal effect. And again, like I mentioned, you have these tidal effects where in the sea you have areas where you get no rises and falls due to tide. Like your
I don't see what tides have to do with this for a Hadley cell. I mean, it's just convection.
but the
wind
data
out of the.
that's the theory, but the data doesn't support it.
Okay, I'm still confused.
Okay.
Hi, my name's Bob Enlick. Spent most of my misspent youth as a weather officer in the Air Force.
Okay.
Okay, so I'm sort of in Dr. Clauser's
Yes.
part of the room.
Okay.
Because it certainly seems, for instance, right here in Tucson, the desert, people come here in the winter because the sun's always shining, and we have in the United States a sun belt. So it seems
Yes.
like in the mean, the vertical velocity is down 23 degrees or 30 degrees or so poleward from the equator. And yes, that we have
Where-
this intertropical convergence zone
Yeah.
that moves north and south, but it certainly seems to fit the weather pattern. And after you answer, I got another one.
Okay, so first of all, when you were going on about the vertical velocity, for a long time, one of the problems they had was, how do you measure vertical velocity? But in these high-quality ozones that we've had for the last 10 years or so, they actually measure the vertical velocity using GPS and various other things like that. And so I haven't put it here, but I have looked at the vertical velocities as you're going up through the atmosphere for all these weather balloons, for these Hadley cell sort of things. And I do find okay, I don't have the slides here. I was just trying to think if I had them somewhere on the computer that I could show you the data, but I don't, so I'll just have to try and talk it through it. The rises that you get that occur underneath the clouds. You know the way the old song Oklahoma, where the wind comes right behind the rain. You know, you get Okay, right, I can actually answer it this way, I think. So what the Hadley cell model says is that the hot air rises and then it hits the tropopause, and because the tropopause is warmer, it goes towards the poles and then comes back down again, right? And then it travels this way. So if you send a balloon up through the middle of that, what you expect to see is the mass flux flowing in that direction down in the lower end of the atmosphere and flowing in the opposite direction at the upper end of the atmosphere. Now, nobody has ever checked to see if that's actually what's happening. So we can analyze the mass flux, and I've summarized in a few words that entire paper, which has passed peer review and that. In fact, I think one of the reviewers said, this data will go down like a lead balloon in some circles, but I don't see anything wrong with the maths. So basically, what we found is that when you go up through the atmosphere, you don't see a change like that. That's what I was showing on the next slide. What you see is at 850, and those are in the lower half of the troposphere, they are flowing. This is the north-south flux. So in other words, I have just taken, because it's a vector, the speed and velocity is a vector, we can resolve it into a north-south component and an east-west component. And so this is just looking at the north-south one, because that's what applies to the Hadley cells. And what you find is that I've averaged these over a running mean, because it moves back and forwards very rapidly in the periods of a couple of days. But this is averaged over 15 days, so you can make some sort of sense of the graph. But what you can see is that the orange and yellow travel in the same direction as the blues. So they should be traveling in the opposite direction if the Hadley cell was correct. And so this is in the Iceland one, but we find for all of the stations that's not the case. They all, at the above the boundary layer is an exception because of the rain and various other things like that, and the mountains get in the way. But once you get up above the boundary layer, which is only about a kilometre high, the rest of the atmosphere should be behaving in the way that the Hadley cell, or that the Hadley cells say, and it doesn't. I mean, that's the data. It's not doing that. We're not finding the blue and the blues and the reds going in the opposite direction. They're going in the exact same direction. So how can you explain that in terms of a Hadley cell? How can you explain that they're all going back and forth in the same direction?
Okay, I understand you need to know more. Can you go to the previous slide? Okay, so this graphic is actually not correct, because the tropopause is higher over the tropics, up around 55, 60,000 feet.
Yes.
And by the time you get into the northern middle latitudes, it comes down to 25 to 30,000 feet. So it's actually slanted down that way. So that's not...
But hang on a second. That's where the tropopause is forming, but the pressures are still the same.
The tropopause is defined as the place in the atmosphere where the temperature stops decreasing.
Yes.
Sometimes, if there's a storm system going by, it's leaved. There's two or three tropopauses because of the storm effect.
Okay. So what I need to say is this: we published again in the peer review. I'm just trying to summarize. See this second one here, right? Here. We compared different tropopause estimates from high and low resolution sondes. And what we found is we have the definition you're giving, which is the WMO definition, is that it's when the lapse rate drops below 2 kilometers, or 2 degrees for a distance of 2 kilometers. And so if it does that and comes back up again, you'll find that you get several tropopauses defined within that. In the tropics, as you know, the tropopause isn't defined that way. It's defined in terms of the low point, the lowest temperature. So all the things you're saying are, the observations you're making are correct, but the theory and the explanation you're giving for them is not working out according with the observed data that we have from the mass flux. That's all I can say. If you like, I'll talk to you again afterwards on it, and I will go into it. Yeah, I'd be delighted to work. And look, I'm a scientist. My view is, if I come up with a theory, it's my job to wreck it, because I'm the one that knows most about it, so I'm the one the most likely to. The old idea of proof, the old meaning of the word proof was to test. So when they said the proof of the pudding was in the eating, they meant it was the test of the pudding is in the eating. So when I come up with these theories, I test them. I want to see, do they work? And I am delighted when nature slaps me in the face and says you're wrong, because then I'm in a position to learn something new. So I'm more than happy if you can convince me that I've made a mistake. Then I can actually do something new. So yeah.
The beginning of what I was trying to say was certainly the weather that we observe in the Sun Belt seems to support the idea that the high pressure about 30 degrees north and south of the equator implies subsiding air.
Okay.
And that would imply that the Hadley cell works. That's all I wanted to say.
Okay.
Hi. Just to try and maybe have some compromise to negotiate, I'm reminded of the I think it was a Hindu parable or something, saying describing three blind men describing an elephant, and so one of them was holding the trunk and describing the trunk. One was holding the snake, the tail, and say it's like a snake, and the other was holding the tusk, and all of them were accurately describing it. And then they could, the other ones were saying, "This is insane." But they all were describing the same thing. And the next thing that I wanted to point out to both, like the commenters there, the Hadley cell is a generalized cartoon sketch that is supposed to be describing what's happening from over a 30-degree latitude. And then there's a similar one for the next 30 degrees and the next 30 degrees. At each point, there's the Hadley cell or the polar cell or the feral cell has a specific predictions. And if you look at an individual thing, you can say, oh, this is consistent with that part of the model. And so being consistent with something, however, doesn't actually prove or disprove it. If it's inconsistent, it might disprove it, but consistent with it doesn't mean that it's proved the larger model. It's when you step outside of the fitting zone, you fit 3 points, or like what's the thing? If you have 2 points, I can fit a straight line to it. So what both Dr. Klauser and I forget your name, Bob mentioned, you were both describing observable prevailing weather patterns, which any comprehensive explanation should be able to do. And then people who've been promoting the Hadley cell said, this is a manifestation of it, and it's consistent with it. And then everyone says, oh, therefore it's proved the Hadley cell. No, it hasn't. It's just shown that it's consistent in that particular localized region. It is consistent with that. And so what we were looking at here is we were said, before we realized, Michael didn't actually mention the significance of the thing, is with molar density, you can actually convert the wind speeds and velocities into mass flux observations. So before that, for 100 years of the weather balloon measurements, it seems nobody had actually thought to plot the molar density. And then when we thought of it, we said, well, why don't we multiply the wind by the molar density, and then you can actually measure the mass flux. So throughout the 50s and 60s and 70s, you look at a lot of the classical, like Chicago group and all of the different groups that were looking at the Hadley circulations and all of these circulations. They were relying on wind velocities and they were saying, well, we don't know what the actual mass velocities are, but because we're only measuring the wind speed. And so they said, but what could you do? And so they said, well, it's kind of consistent with it in this level. What we realized is that with the molar density, you can actually convert those wind measurements into mass flux measurements. And so for the first time, we were actually able to do it. And we were totally shocked. In that paper, to try and get past peer review, we tried to minimize how much we were going against the paradigms, because we found that, like, when you're trying to get a paper published, you can only really criticize one or two paradigms at a time. So we said, okay, we'll just look at these 5 things. But we've looked at hundreds all around the world. People are not looking at this, and we're like, we first published about this molar density in 2014. So that's more than it's more than 10 years, and we're like, it's very easy to calculate the molar density from the data. You just download, okay, it's not very easy, but if you've undergraduate physics or maths, you can calculate the molar density. And anybody that's kind of skeptical about the stuff, which I think there's a good way to be, don't believe us just because we're saying it, but do have a look at go find a weather balloon from your local station and download it, put it into Excel, use the formulas to do it, which is basically the ideal gas law, and just have a look.
There it is there, right?
Yeah.
We have the pressure measurements from the balloon data, we have the temperature measurements from the balloon data, and R is the gas constant. And if we take our volume as being 1 cubic meter, that gives us the molar density. So it's a simple thing to do. So you can get the molar density from the weather balloon data at any region where you have a balloon measurement. And when you know the molar density, the number of molecules that are in the volume, then you can calculate the weight, because we know what the mass of oxygen is, we know what the mass of nitrogen is, and so on. And so we can actually get the mass flux, which is we're the only ones that have ever actually done that measurement. And so what we're saying is, when we did that measurement and we look at the actual result, we don't see Hadley cells, we don't see Farrell cells. What we see instead is a large pendulum, the air moving all in the one direction, one way and back, except at ground level. So on the lower half mile or so, there you get different patterns occurring because of mountains and various other things like that, and cloud formation. So that's all right. Okay.